This next method is integration by trigonometric substitution. You'll recognize when to use this if you have a square root of an a squared plus or minus x squared, or maybe a square root of x squared plus or minus a squared term inside your integrand. And if you do have one of those, this table here shows which substitution you would want to make. So if you have, for example, a square root of a squared minus x squared form, then you're going to want to let x be a sine of theta. If you have a square root of a squared plus x squared form, then x is a tan theta. And the third one is if you have the square root of x squared minus a squared, then you'd let x equal a secant theta. And so here I'm going to demonstrate how to actually apply this approach. This first example is the integral of the square root of x squared minus 9, all divided by x squared. And so here we have an x squared minus a squared form where a is 3. And because this has the form of the third entity in the table, the third row, I'm going to let x be a secant theta, or in this case, 3 secant theta, which means that x is 3 secant theta. And so that's going to replace the x, but we also need to figure out what to substitute in for the dx. So dx is going to be 3 times the derivative of secant theta, which is secant theta tan theta. And at this point, I'm going to make the substitution. So in the numerator, we have 3 secant theta squared, which is 9 secant squared of theta minus 9, all divided by 3 secant theta quantity squared. So we have a 9 secant squared theta on the bottom. And then the dx is 3 secant theta tan theta d theta, and I forgot to put the d theta in over here, so I'm just going to squeeze that notation in because it should be there. And from this point, now I want to start simplifying. And so I see that the square root term I'm going to factor out that 9 and pull it out of the square root. So I'm going to have 3 times the square root of secant squared theta minus 1. On the bottom, we have 9 secant thetas. 1 secant disappeared because of the 3 secant tan theta on the outside, so I divide a secant on top by one of the secants on bottom, which still leaves us with a tan theta d theta. And now I look at that secant squared theta minus 1, and I realize that comes from an identity. That is going to be tan squared theta. So this is 3 times the square root of tan squared theta over 9 secant theta times times 3 tan theta. I lost a 3 on the previous part. So there's a 3 here, but a 3 also came by taking the 9 out of the square root. So there should be a 3 term here. Notice that those 3's are going to become a 9 and cancel out with a 9 on the bottom, so it does simplify a little bit more. The square root of tan squared is tan theta times the tan theta that's in the problem. And this is going to give us tangent squared of theta on top and a secant theta on bottom d theta. And so at this point, we've simplified it. Let's see where we could go from here. So you could either convert the tangent into a sine over cosine and the secant into a 1 over cosine. That won't necessarily help, but what we can do is I'm going to use an identity for tan squared, and I'm going to go back and say that tan squared is secant squared minus 1. So this is going to become secant squared theta minus 1, all divided by secant of theta, and this is d theta. I'm going to divide through, and this is the integral of secant theta minus 1 over secant, but secant is 1 over cosine, so 1 over cosine is just cosine of theta d theta. And you could distribute this integral as such, and then from here you would integrate both parts. The first one is equivalent to the natural log of secant theta plus tan theta. And that, if you've never seen this integral evaluated, that could be used by the trick of multiplying by 1, where you're going to multiply that secant theta by 1, where 1 is secant theta plus tan theta divided by secant theta plus tan theta, and then you're going to make use of u substitution. So that's a common one to demonstrate, usually in Calc 1 or when integration is first introduced. This second integral is a more fundamental one. The integral of cosine theta is going to just be sine of theta. And you have your plus c. And it feels like we're done. However, here our answer is in terms of theta, whereas our original integral was a function of x. So we want to somehow convert back into an answer of x. And the way that we're going to do that is we're going to look back at the very beginning here, where we had defined x as 3 secant theta. And so I'm going to use a triangle in order to figure out some of these details. And I'm going to do that by realizing that secant theta, which is 1 over cosine of theta, is x over 3, which means cosine of theta is 3 over x. And so if I sketch a right triangle where this is theta, then using SOHCAHTOA, CA, C-A-H, cosine is the adjacent, which is here, over hypotenuse, which is there, which means that the remaining side is going to come from the square root of x squared minus 3 squared, or x squared minus 9. Now I've got all of these terms, and I'm going to make use of that because I need to substitute in for secant theta. So this is the natural log of secant theta is x over 3 based on our substitution. Tan of theta is TOA, SOHCAHTOA, so that's going to be opposite, which is the square root of x squared minus 9 over adjacent, which is 3. So this is square root x squared minus 9 over 3 minus the sine of theta. Sine is SO, or opposite, over hypotenuse. So this is the square root of x squared minus 9 over x, still our plus c. And here's our answer. Let's do another one and continue practicing with this. You'll see that this second integral has a square root of an x squared plus a squared form. So looking at this table, that is related to the second expression. So we're going to let x be a tan theta, where a comes from the square root of 4. So that's going to be 2 tan theta. So over here, x equals 2 tan theta, which means dx equals 2 secant squared theta d theta. And so when we make the substitution, we have an x squared on the bottom, so we have 4 tan theta. And we have the square root of 4 tan squared theta, and that tangent outside should also be squared, plus 4 inside the square root. This is all in the denominator, and dx is 2 secant squared theta d theta. So let's start simplifying wherever we can. So this is the integral of, we have a 2 secant squared on top, we have a 4 tan squared on bottom, I'm going to pull the 4 out of the square root. I'm going to factor it, and so that's going to give us a 2. And we have the square root of tan squared theta plus 1. And this tan squared of theta plus 1 is equivalent to secant squared which means we're going to have 2's cancel out on top and bottom. We are also going to have a secant squared theta on top. We have 4 tan squared theta, and we're going to have the square root of secant squared, which gives us secant of theta. And so one of our secants cancel out. And so now we need to figure out how to manipulate this integral here. The 1/4 can come out, and then you have a secant. There's no substitution for the secant. You also have a tan squared on the bottom. Converting the tan squared into a secant squared minus 1 won't help because you can't cancel the numerator by both parts of the denominator. So I'm going to see what happens when we convert these into their sine and cosine forms. What we get, again, I'm going to pull the 1/4 out. Secant theta is 1 over cosine of theta. The tan squared becomes sine squared over cosine squared. And this seems promising, and so multiplying the numerator by the reciprocal of the denominator, what we get is a cosine theta on top, a sine squared on bottom, and that's it. So this looks good because I recognize that since I have just a cosine on top, if I let u be sine, not sine squared, that's going to give me a du in terms of cosine. So that's exactly what I'm going to do here. I'm going to use u substitution where u is sine of theta, which means du is cosine of theta d theta. And this, after substituting, gives me 1/4 of the integral of 1 over u squared. And cosine theta d theta is du. So 1 over u squared is u to the negative 2, which gives me negative 1/4 times 1 over u, or negative 1 over 4 u plus c. U is sine of theta, so this is negative 1 over 4 sine theta plus c. So I need to figure out what sine of theta is in terms of x. So I'm going to, again, make a triangle. Here's my theta. Our x was 2 tan theta, which means tangent is x over 2. Tangent is opposite over adjacent. So opposite is here, adjacent is here, which means we have the square root of x squared plus 4 for our hypotenuse. So sine is going to be opposite over hypotenuse. So opposite is x, hypotenuse is the square root of x squared plus 4. When I make this substitution, we have negative 1/4 times 1 over sine, or 1 over x over square root of x squared plus 4. But I'm going to multiply by the reciprocal, which is going to be the square root of x squared plus 4 over x. And we still have our plus c lingering. And this is our answer to this second problem here. Let's look at number 3. This third problem wants the integral of t over the square root of 3 minus 2t minus t squared. At first glance, this doesn't look like it has any of the forms that we want, but maybe if we complete the square, that would be useful. So I'm going to complete the square on top. So 3 minus 2t minus t squared. What does this look like? I'm going to keep the 3 there, minus, and I'm going to look at 2t plus t squared. It would be really handy if that were just simply 1 plus t squared. 1 plus t squared, I know that's going to give me a t squared. It's going to give me a 2t, but it also gives me this plus 1. So I need to also subtract that plus 1. But notice that after I distribute the negative sign out front, that's going to give me a negative 1. So to have that negative 1 disappear, this is actually going to have to be negated. And so that means that it becomes 4 minus 1 plus t quantity squared. So this is what I'm going to work from. I'm going to rewrite this integral as t over the square root of 4 minus 1 plus t squared dt. So it has a square root of a squared minus x squared type form. And a squared minus x squared has an x equals a sine of theta, but x in this case is 1 plus t. So I'm going to let 1 plus t equal 2 sine theta, which means that dt equals 2 cosine theta d theta. Now when I make these substitutions, t on top becomes 2 sine theta minus 1. On the bottom, we have the square root of 4 minus, and 1 plus t is 2 sine theta. So when I square that, I've got 4 sine squared of theta. And dt is 2 cosine of theta d theta. And so now I need to start simplifying wherever I can. So on top, we have a 2 sine of theta minus 1. This is multiplied by 2 cosine theta. On the bottom, we have a 4 that can be factored and pulled out of the square root, so that's 2. And that's going to leave us with 1 minus sine squared, which is equivalent to cosine squared by an identity. The square root of cosine squared is cosine of theta. So you can see that some things start canceling out very nicely. So we have a 2 cosine theta on top and bottom, and we are left with integrating 2 sine theta minus 1. So now we want to integrate this, and we've got the integral of sine of theta is negative cosine, so we have negative 2 cosine of theta minus the integral of 1 d theta is theta plus c. And again, we need to somehow convert these into functions of t in this case for this problem. So sine of theta is 1 plus t over 2, which means that in our triangle, sine is opposite over hypotenuse. So opposite is the 1 plus t. Hypotenuse is 2, which means adjacent is the square root of 2 squared, or 4 minus 1 plus t quantity squared. So now we need cosine. So cosine is, so ca, that's going to be adjacent, which is the square root of 4 minus 1 plus t quantity squared over hypotenuse, which is 2, minus theta, and theta is going to come from our 1 plus t equals 2 sine theta. So you're going to solve for theta, and that's going to come out to the arcsine of 1 plus t over 2. You could simplify a little bit by canceling out the 2's, but this essentially is our solution to the third problem. And again, just in case you're not sure where that arcsine came from, I used this substitution in order to solve for theta. There's one last problem. As the integral of v squared, or square root of v squared minus 25 dx. Again, if we look back at our substitution forms, that was v squared minus 25, and so that has an x equals a secant theta form. And so I'm going to let x be 5 secant theta in this case, which means dx equals 5 secant theta tan theta d theta. And then I make my substitution. So we have the square root of v, that these should be v's. So v equals and dv equals. So v is 5 secant theta, which means this is 25 secant squared of theta minus 25. And the dv, this should be a v, dv is 5 secant theta tan theta d theta. And now we start simplifying. So I'm going to factor out that 25 from the square root, which is going to become a 5. This is the square root of secant squared minus 1 times the 5 secant theta tan theta d theta. And then you may recall that secant squared theta minus 1 is equivalent to tan squared theta. Which is going to give us a 5 times 5. I'm going to pull 25 out. Square root of 10 squared is tangent. So inside the integral, we have a secant theta times 10 squared of theta d theta. And so now we need to figure out how to get this derivative or this integral. Looking at this, there's no clear u substitution. If I let u be secant theta, du is going to be secant times tangent. So there's one secant short and one extra tangent. If I let u be tangent, then du is going to be secant squared, but we only have a single secant, so that doesn't seem to work. So then I might look to consider consider 10 squared as secant squared minus 1. All right, so that means we have 25 times the integral of secant theta times secant squared minus 1. So it's going to be secant cubed theta minus 1 times secant theta. D theta. And if you integrate this, you might get stuck with the integral of secant cubed, but you can integrate the second one there. And so that, again, we saw that in an earlier problem. That's going to be the natural log of secant theta plus tan theta. So let's progress and see where we can get to. So we have 25 times the integral of secant cubed theta d theta minus 25 times the natural log of secant theta plus tan theta plus c. So far so good. We still need to try to figure out how to evaluate this secant cubed. If we pull out a secant squared, what is that going to do for us? Let's check it out. I'm going to do that down here. We want the integral of secant cubed theta d theta. I'm going to view this as the integral of secant of theta times secant squared theta d theta. And I see this as a product, and when I think of an integral of a product, I think of integration by parts. So I need to figure out what to let my u be and what to let my dv be. And looking at this, I know that the integral of secant squared is tan, so it would be convenient to let that be dv. and the other part be u. So I'm going to let u be secant theta, and dv, I'm going to let be secant squared theta d theta, which means du is secant tangent and v is tangent. So integration by parts is uv, which is secant tan in this case, minus the integral of v du. So that's going to give us secant times tan squared and this all stems from, let's see, tan squared, remember, is secant squared minus 1. So this is secant theta tan theta minus, we have the integral of secant theta times secant squared minus 1. So that gives me secant theta tan theta minus the integral of secant cubed theta d theta. And then you're going to have two minuses, so that's going to be plus the integral of secant d theta. And I'm going to use a trick that you saw back with integration by parts, where we evaluated the integral of e to the x sine of x dx. And the trick was that we ended up getting an integral that was on our left and on our right. And so over here, remember, this stems from the integral of secant cubed. And we have an integral of secant cubed here. I'm going to add that integral of secant cubed to the left side, which is going to give us 2 of the integrals of secant cubed. And what's left on the right is secant theta tan theta plus the integral of secant theta, which is the natural log of secant plus tangent. And so when we solve for the integral of secant cubed, that's what we get. Now, why was that important? Because it's kind of been a while. Integral of secant cubed we have over here. So we want to substitute that in. We're going to get, let's see, 1/2 secant theta tan theta. There's a 25 out front. So it's 25 halves, or 12.5 secant theta tan theta that 25 is also multiplied by the 1/2 times the natural log of secant plus 10. So that is plus 12.5 times the natural log of what I had just said, secant theta plus tan theta, minus what we had here, which is minus 25 of the natural logs. So we had plus 12.5 minus 25, which for simplicity is going to change this into a minus sign, plus our constant. So finally, we need to figure out what secant and tangent are in terms of x. Remember our substitution, in terms of v, our substitution was that v is 5 secant theta, which means secant theta is v over 5. So some of this we could get pretty quickly. We've got 12.5 times v over 5 minus 12.5 times the natural log of v over 5 plus something that we haven't figured out just yet. So we need to figure out what tangent is. So let's draw our right triangle. All right, so secant theta is v over 5, and secant is 1 over cosine. That means the reciprocal is cosine of theta is 5 over v. So cosine is adjacent, which is 5, over hypotenuse, which is v, which means that this remaining side is the square root of v squared minus 5 squared, or 25. So tangent is opposite, which is the square root of v squared minus 25, over adjacent, which is 5, and this is our final solution. And that's it. It is a tricky method to do, but a useful one to know. You'll get more practice in homework, and let me know if you have any questions.